Drude model for metals. The first thing we'll do is we'll derive the Drude model, and what we'll see is that the Drude model really is the Lorentz model where we've eliminated that restoring force. We'll talk about plasmons and the plasma frequency finally, and then make some notes and observations about the Drude model. Let's go ahead and derive the Drude model. So we start with the Lorentz oscillator model for dielectrics. But now in a metal, these electrons are easily lost. They're no longer bound to the nucleus, so they don't have that restoring force. So in fact, if we go into our Lorentz oscillator model and just set that resonant frequency to 0, we get the Drude model for metals. Our equation for plasma frequency does not change. We can interpret things a little bit differently now. N is now interpreted as the free electron density, and I'll write that as N sub E from this point forward, just to make that note. Me is still the mass of an electron. And to give you an idea for plasma frequency, the typical plasma frequency, I'll say 10 to the 16. It's usually in the extreme ultraviolet for metals. So that is super high frequency. We'll make one more change to the Lorentz oscillator model other than eliminating omega naught squared. Rather than use this gamma term, we're going to use this term tau, and that is called the mean collision rate, also called sometimes the momentum scattering time. But if we imagine an electron traveling in a metal, there's a certain amount of time that travels before it bounces off of something. And of course, there's a whole bunch of electrons that are traveling on randomly, and it's a very statistical thing. But this mean collision rate, or the mean time between collisions, is this tau. And so for metals, that becomes more meaningful. But in terms of how it's used in the equations, it's just 1 over the gamma term that we were using for dielectrics. To give you an idea of numbers, in metals, the collision rate is on the order of 10 to the minus 14 seconds. So that's a very quick amount of time. One thing we did with the Lorentz oscillator models, we looked at the real and imaginary parts, and it's even particularly important for metals because this will lead into discussion of conductivity. So we start off with our Drude model that gives us our complex permittivity, and through a series of math, we can arrive at the real and imaginary parts of permittivity for the Drude model. Step you roughly through the derivation. I won't spend a whole lot of time on that, but it's the same trick. We have a complex number on the denominator, so we have to multiply by its complex conjugate. We don't want to change it, so we need to multiply by 1, so it's the complex conjugate on numerator and denominator. But when we multiply, we get a completely real number on the denominator. We end up with some terms on the numerator that we can separate into real and imaginary parts, and we end up here, and we can identify the real part of permittivity and the imaginary part. But the derivation's there, and I welcome you to work through that yourself. But in the end, we end up with the real and imaginary parts of permittivity for the Drude model. Now, what about the ideal metal? The ideal metal, the electrons won't crash into anything. They just travel forever in a straight line, because every time they crash, then energy is going into that crash and not going into conduction, and that leads to loss. So the ideal metal, that tau term goes to infinity. And if we set tau to infinity in the Drude model, this is what we get. And it turns out the imaginary component goes exactly to 0, and we just have a real component to our metals for the ideal case. And we would actually call this a free electron gas. And if we plot the response of an ideal metal, what we see is that the permittivity is very, very negative at low frequencies. At around the plasma frequency, it passes through 0 and then slowly goes up to 1. And in metals, we tend to think of the plasma frequency as sort of a switching point, where below the plasma frequency, it's acting like a metal, and above the plasma frequency, it's acting like a vacuum. And of course, there's not a distinct cutoff, but that's one sort of way we can interpret the plasma frequency. Let's think of the Drude model in terms of the electrical conductivity. So we really have 2 ways of specifying materials with loss. In one world, we have a complex permittivity. In another world, we will have a real valued permittivity and a real valued conductivity. So how do we get there? Well, we have Ampere's circuit law. So we have our current density and we have our displacement term. Well, our current density is sigma times E. That's sort of Ohm's law for electromagnetics. And we can replace this displacement field or the electric flux with the electric field intensity simply by using the constitutive relation. So now we have the permittivity times the electric field. If we compare these two sides, now we can see that on one side, we have a real and an imaginary component for a complex permittivity, or we have a real valued permittivity and a real valued conductivity. And we can think of it as sort of conservation of information. In both schools, both ways of doing things, we have two numbers. Now, I also have seen where we have a complex permittivity and a conductivity, and I think that's really confusing, and I will never do that. But just beware, stuff like that is floating out there. But in general, these are the two ways to specify a material. So let's relate these systems so we can calculate one from the other. So what we'll do is both are equaling del cross H. So we're going to set the left side of this equation, or sorry, the right side of this equation to the right side of that equation. We set those equal. Now what we can do on the right-hand side is factor out the electric field on the right, and we can factor out j omega epsilon naught on the left. And so we're left with this expression in parentheses from what happened on the right side of this equation. Well, now if we compare both sides, whatever's in parentheses here must be the same thing as the complex permittivity. So that's exactly it. Complex permittivity is the real valued permittivity plus here's our conductivity divided by j omega naught. So the real valued permittivity is the same thing as the real part of the complex permittivity, and the imaginary part of the complex permittivity comes from the conductivity, but divided by omega epsilon naught. And we can use those equations to convert between those two schools of thought. So now we can write an expression for the conductivity that comes from our Drude model. And so we had this expression on the previous slide that related the imaginary part of complex permittivity to conductivity. So we solve that for conductivity, and we get this. Well, from previous slides, we had an expression for the imaginary part of the complex permittivity, and we can plug that in here and simplify a little bit, and we end up with our final expression for the conductivity according to the Drude model. We can think of also a DC conductivity. So on the previous slide, we got this expression for our conductivity from the Drude model. Well, at DC, we set that omega term equal to 0. And we reduce, so we set that to 0. So we'll see that this goes to 0. We'll just have a 1 in the denominator. And in fact, we're just left with the expression in the numerator. Well, that is the DC conductivity. We'll give that a special symbol. We'll give that sigma naught. So conductivity at DC. And now we can rewrite the Drude conductivity with the DC conductivity term in here. And that really tells us the frequency dependence. It tells us what happens to the conductivity as frequency increases. So it starts off at this, and then what we see is that the conductivity will go down at higher frequencies. Let's make a bunch of notes and observations about the Drude model and what we've learned. So here is a plot of the typical Drude response along with the conductivity. A lot going on here, so let's just look at this one at a time. So first, we'll look at the real part of the permittivity. That's the blue line here. And what we can see is that below the plasma frequency, the permittivity, the real part of the permittivity becomes negative. And in fact, we can set the frequency term equal to 0 and derive a handy little expression of what the value of that is, and it's 1 minus this something, and this something is why our permittivity becomes negative below at about the plasma frequency. We can see it's not an exact thing, but below the plasma frequency, our permittivity becomes negative. And here's actually the most attractive mechanism to realize a negative permittivity. And later on, when we get to metamaterials, we're going to want a negative permittivity and a negative permeability, and this is a big hint about how to do that. Then if we look at the imaginary part of the complex permittivity, that goes off to infinity. That shows that metals are incredibly lossy below the plasma frequency, particularly as it approaches DC. In fact, metals become so lossy, they're no longer lossy. And what do I mean by that? There's so much loss, the parameters are so extreme that the wave just reflects off the metal and never actually experiences that loss. Above the plasma frequency, we see that the loss, it takes a while, but it eventually goes to zero, and way off at a super high frequency, well above the plasma frequency, things are acting like a vacuum again. And we expected that because the Drude model really is just a special case of the Lorentz oscillator model. But it takes a while. So actually, at frequencies just above the plasma frequency and a good distance out, we really would best describe these materials as weakly absorbing. And so we can roughly think of the plasma frequency as a switch, if you will. At frequencies below the plasma frequency, metals act like metals. We get a super negative permittivity and waves reflect from metals. Above the plasma frequency, they are transparent. We could see this is not a real sharp cutoff, but that's one way of thinking about the plasma frequency. And in a following video, we're going to get more into the plasma frequency, what's actually happening there. Then the green line is our conductivity. And what we can see is that at DC, we get our DC conductivity. But if we go way out to infinity, way above the plasma frequency, our conductivity eventually goes to zero. And that's consistent with the metals acting like a vacuum at frequencies well above the plasma frequency. But remember, these plasma frequencies are usually in the extreme ultraviolet. So by super high frequencies, we're talking about X-rays and things way up there before metals look transparent. We can plot the refractive index and the attenuation coefficient. So the ordinary refractive index is shown in blue here. And what we can see is, around the plasma frequency, we're getting a negative refractive index again. But at DC, that ordinary refractive index goes way up to infinity. So refractive index of metals at very, very low frequencies is extremely high. The same thing about this extinction coefficient that's characterizing our loss. That also goes to infinity at DC. But I'll mention it again, the loss in metals is so high at low frequencies that they're actually no longer lossy, and that's because waves reflect from them because they have such extreme parameters, so they never really get to experience that loss. If we plot the attenuation coefficient, which is really the better measure for loss, we get this black line. And it approaches zero as we go out to infinity. But what we can see is that we get very high attenuation at frequencies below the plasma frequency and moderate attenuation coefficient at frequencies above the plasma frequency, but it does eventually go out to zero. I've pretty much have made all the observations, but let's go ahead and just talk about them one at a time. So well below the plasma frequency, the dielectric constant's mostly imaginary, and the metals behave like good conductors. So for the most part, if you're well below the plasma frequency, you have nothing to worry about. The metal will act like a metal. Near the plasma frequency, this is a really, really tough place to operate with metals. And this is challenging for optical frequencies because they are approaching the plasma frequencies, and metals are a big problem at optical frequencies. And optics people tend not to like to use metals for that reason. And when they do, they have to combat the loss of those metals. So we tend not to like to operate metals near their plasma frequency, but you know what? We don't have a choice. We can't design atoms and molecules to be different. But along comes metamaterials, and actually we can do some things that are quite different. Well above the plasma frequency, for the most part, metals become transparent, but to be more accurate, we would call it weakly absorbing. If they didn't absorb at all, then X-rays would not be able to image our teeth and bones and body organs and stuff like that. So it is weakly absorbing, and that's actually a very useful thing for us in order to image things.